We're now going to study how to display the distribution of a numerical variable. Before we do that, let's recap how to display the distribution of a categorical variable. A distribution consists of two connected lists, the distinct values of your variable, and the frequencies of all those different values. We use the group method to count the number of individuals in each category. In our example, it was the number of movies released by each studio. And then we used a bar chart to visualize. There was one bar for each category, and the length of the bar was the count of movies in that studio, that is the count of individuals in that category. We'll do something very similar for numerical distributions, but before we do that, it's a good idea to look at a general principle of visualization that we should keep in mind whenever we look at a visualization or make one. And that's the area principle, which is perhaps best understood by looking at an example. Here's a visualization we found from the visualization website called Flowing Data, and it describes a graphic representing the change in battery size from an old iPad to a new one. And the numerical data is that the new battery is supposed to be 70% bigger than the old one. And the text says, something's not right here. And indeed, something does feel a bit off when you look carefully. It's true that this one is bigger than this one. But how much bigger? It's supposed to be 70% bigger. Well, if this one gets 70% bigger, it won't double in size. To double in size, it would have to get 100% bigger. Yet this battery clearly can hold more than two of these little ones. It is more than double the size of the little battery. And here you notice something. What your eye is picking up as size is area. Not height by itself, not width by itself, but area. What has happened here is that the vertical height of this new battery is indeed 70% more than the height of the old one, and the width of the new battery is indeed 70% more than the width of the old one, but they shouldn't have increased both dimensions. Because when you increase both dimensions, the area increases even more, and then your figure just looks too big to the eye. So the area principle says that areas should be proportional to the values that they represent, because your eye picks up area. For example, if you choose to represent 20% of a population by this triangle here, then you can represent 40% by two of those triangles, but not by one huge triangle where you have doubled both the width and the height. That's too big. That huge triangle will actually hold four of these little ones. It's doubled in both dimensions, and hence its area has gotten multiplied by a factor of 2 times 2, which is 4. And even if you don't want to think about that math, just keep in mind that you shouldn't be changing the size of multiple dimensions. It makes diagrams difficult to interpret. We will keep the area principle in mind when we look at diagrams and also when we draw our own. Here's an example where we're going to look at a visualization and ask you a question. Is this visualization consistent with the area principle? What does it represent? It represents the amount of sales at various fast food franchises. Each franchise is represented by its logo. The logos have various different shapes. And what appears to be happening here is that the more the sales, the bigger the logo has been drawn. And the question to you is, have those increases been consistent with the area principle? I'll give you a suggestion for how to compare areas. I find it really hard to compare areas of disks, circles. It's much easier to compare areas of things that look like rectangles or squares. So find the rectangles and squares on things that sort of look like rectangles and squares, even if they aren't exactly, and try to compare those, keeping in mind the numerical data that are also provided. You're trying to see whether the area principle has been followed. Pause the video. We'll come back after the countdown. 3, 2, 1. I will compare this KFC logo with this Taco Bell logo just because that's a square and that's a kind of a rectangle. Not quite. It's got a curvy top. The numerical data are that the Taco Bell number is 4.3 and the KFC number is 8.2, so almost double. Not quite, but almost. 2 times. The picture doesn't say that to me though. The logo, this logo, if I take it and imagine it going here, I can fit more than 2 of them in here. So the area of this KFC logo is more than twice the area of the Taco Bell logo, whereas the number 8.2 is not quite twice the number 4.3 for Taco Bell. So the area principle has not been followed. And that makes the graph somewhat difficult to interpret. Perhaps just plotting a bar graph of these different numbers would have been easier to understand.